Hello everyone, this is Peter here. I'm going to go through the KAS block exam 2017 for physics. Okay, right, so the first question. We should have got this one right. Velocity time graph. The constant velocity on the graph is shown by this horizontal part of the graph. Let me change pens to a blue pen. The horizontal part of the graph. B. The distance travelled is shown by, you should remember this, if you've got a velocity time graph, the area underneath the graph shows you the distance travelled. A. And for the average velocity, if you want to work out the average velocity, you take the distance and divide it by the time. That's going to be B. Nice one. So this is going to be BAB for question 1. I've got the mark scheme here. I didn't want to show you the mark scheme for question 1 because it literally just said BAB. It was pretty boring. Question 2. What do all these things do? I'm not going to go through the rest of the question. It should be high resolution enough that so you can read it if you want to press pause. A coolant removes energy from the reactor. The fuel rods contain uranium for fission, the uranium fuel, and shielding absorbs dangerous radiation. This is the shielding bit on the outside, and we need to get all of those bits. For question B, I've actually got the original paper that we took this from, and what you can see is we actually removed one of the questions about energy because we haven't taught energy yet. So for part B, you had to explain what the moderator in a fission reaction actually does. But what the moderator does is it slows down neutrons. It slows down neutrons, otherwise they go too fast and they've got too high energy to actually be absorbed by uranium. So that they can be absorbed by the uranium fuel. Causing fission. Explain, in terms of the neutrons, what is meant by controlled nuclear fission. Okay, so controlled was the word that seemed to puzzle a few people in this question. And the reason it puzzles is because people started speaking about control rods and just talking about control rods and didn't talk about nuclear fission, or they just spoke about nuclear fission, didn't speak about the control rods. You've got to do kind of everything all in one. Nuclear fission can take place in an atomic bomb. What makes it different in a nuclear reactor is we control it. We control it and we slow it down a little bit, and we control the chain reaction. So first of all, let's explain what nuclear fission is. So a neutron, can't spell neutron right, I have to add that E, oh better. Neutron is absorbed by uranium nucleus. Fission occurs, releasing energy, lots and lots and lots of heat energy. Daughter nuclei and neutrons, 2 or 3 neutrons. Then these neutrons cause further fission events, and they can be slowed down. Well, they could be, sorry, not slowed down, they could be absorbed by control rods instead of the fuel. So lowering the rods, we should probably say control rods to distinguish it from fuel rods. So control rods, lowering control rods causes more neutrons absorbed by the rods slows rate of fission. That's how I would have explained it. Mark scheme, what does it say? This is part B, wasn't included. This is part B, this is part C. So each fission is caused by a single neutron. Each fission releases more than one neutron. We've got that here with the 2 or 3 neutrons. Excess neutrons can speed up the reaction. So more neutrons cause further fission events, speeding up the reaction. Fission releases excess energy. I've got energy there. Control rods absorb the neutrons. Control rods regulate the rate of fission. So lowering the control rods basically slows down the fission reaction. So that's question 2. Question 2, go on. Question 3. Different types of waves are used in hospitals. Which of these properties is the same for all EM waves? So here's the question, here's the mark scheme. Which one is the same? It's the speed of light. They all have the same speed of light. Gamma rays, we should know about these, and microwaves and X-rays. So X-rays imaging broken bones. You don't really need to be in a lesson to know that. Microwaves heat up food. Again, kind of easy. Gamma rays, medical traces. It's the only one that's a little bit more complicated, but we've done a lot of traces already. Electromagnetic waves are transverse waves. That's what we should be thinking. Describe how vibrations of transverse wave relate to the direction in which the wave travels. I like to draw a diagram. This is my wave. Okay. And this is wave traveling. And these are the vibrations. So the vibrations are at right angles to the direction the wave travels. Vibrations, right angles or perpendicular to direction that the wave travels. And it's pretty much got that here. Direction of vibration is perpendicular to the direction the wave travels. Allow at right angles or allow at 90 degrees. So perpendicular is a better word to use. I should have really used that. Question 4. Oh no, sorry. Question 3, part B. Another type of wave is used in hospitals. Ultrasound. We need to remember this. We can hear from 20 hertz to 20,000 hertz. Must remember this. That's the bassy sounds, that's the high-pitched sounds. Anything lower than this is called infrasound. Anything higher than that is called ultrasound. You don't need to memorize this number, 45,000 hertz. You just need to remember this. That's when we can hear. All of these frequencies we can hear, so they're not ultrasound. The only one that is part D. A technician calculates the depth of reflection from when a wave is emitted to when reflection is received. Explain why you use this value half. So why do you use half? Well, you use half because what happens is when, imagine this is the surface of someone's body, and here we've got something that the ultrasound is going to bounce off. The ultrasound is going to go to that object and then bounce back again. It's going to go all the way there and back. And in order to work out just the depth, you're basically just trying to work out the way there. So you just want to find this distance here, the depth. So you could say the wave travels there and back. I.e. 2 times the depth. Even a little diagram like that could help. So you need to divide it by 2. And if you look at the mark scheme, the wave travels there and back. Depth is half the total distance travelled, or what I've written, which is the wave travels 2 times the depth. The time in that case to go to the actual target in here is half of the total time it takes for the wave to travel. So those types of things will get you the mark. We didn't include this question. And we are on question number 4, which was originally called question 9 in the original paper. So, where are we? Tritium, 3, 1. That's really hard to see in the video, so I'm just going to make it a little bit bigger. 3, 1. We need to remember a few things. This is our A number, our mass number. This is our Z number, which is our atomic number, which is the number of protons. The number of protons is 1. The number of neutrons is going to be 3 take away 1. It's going to be 2. 3 differences between an alpha particle and a beta particle. Okay, all right. There's so many things we could say. So, alpha and beta, I'm going to do a quick table. Alpha, 2 plus positive charge. And it's really easy for you to lay out your answer like this. If you can do that, then it makes it easier to get marks. Don't write massive paragraphs. It's easier to do bullet points or to do something like this. So you can say this is a 1 minus negative charge. You could talk about what they are. This is 2 protons, 2 neutrons. This is 1 electron. This is high mass. I'm not going to put the actual value in. This is very low mass. We could also say lots of other things. High ionization, or very high ionization. Medium ionization. What else is there on the mark scheme? So we could say negative and positive. We said that. Low and high mass. We've said that. Beta particle has 1 charge, 2 charge, 2 plus, 1 minus. So if I've written down 2 plus positive charge, 1 minus negative charge, that's 2 points already. Beta particle is an electron, and alpha is just 2 protons and 2 neutrons. Beta is less ionizing. Beta has a high speed. You could have said that as well. Beta particles have a larger range. They go further. In air, for example, they go a meter, whereas alpha only goes 1 centimeter in air. Beta has higher penetrating ability, so it can go through paper. Alpha can't go through paper. Why can tritium not emit an alpha particle? Well, an alpha particle is 2 protons and 2 neutrons, and tritium is 1 proton and 2 neutrons. You can't get an alpha particle out of it. So loads of people wrote down only 1 proton in tritium, and I think that's fair enough. I think that's a good sensible suggestion. Here's loads and loads of stuff in the mark scheme. You should be able to pause it and read it if you want to. So part B is not part B in this, because we took out an energy question. So this is actually part B, and that's part C. So part B, explain what is meant by half-life. Time taken. I've said this to you plenty of times. If you say time taken, you get 1 mark automatically. Time taken for the activity of a substance to reduce by a factor of 2. You could also say it's the time it takes for the number of nuclei that are radioactive to decrease by a factor of 2 as well. So mark schemes there. Use the graph to estimate the half-life of tritium. So what we do is we take our original value and we see how long it takes to go to half of that value. So I'm going to go from 1,200 to 600. And I draw clearly on my graph. Don't forget to do this. A line that goes there, and a line that goes there. I should really use a ruler. Apologies. It's around about 13.5 years. And there's 2 marks here. 1 mark is for the graph. 1 mark is for writing down an answer. So if you've just written down the answer without actually doing the working, you won't get the 2 marks. So 13.5 years plus or minus half a year. So 13 years, 14 years is fine. Part C, the manufacture of the luminous sign. Okay, the reason it says luminous sign, by the way, is because we took out part B where there was a luminous sign, but it doesn't really matter. There's a luminous sign that contains tritium. Says that the sign will work for more than 20 years. Is it correct what he said? Oh, we need to bring this back. Well, 20 years if it's 20 years, then the activity would be a little bit higher than 400, and around about 420, I'd say. And another way to look at it is to say, well, 400 would take about 21.5 years. So, yes, he's completely correct. And the mark scheme doesn't want you to just say, yeah, it's still going to be carrying on a little bit longer. To get that second mark, you actually need to say a value for what the activity would be at 20 years. So because at 20 years the activity would be higher than 400, exactly 420, or anywhere between 410 and 440 would be fine. Or you could say the activity is 400 at somewhere between 21 and 22 years. If you say that, then you're also that's also worthy of a mark. So yes is only 1 mark. The second mark is to explain why, and you have to actually use numbers to show it. So where are we? Question 5. Add a voltmeter to the circuit diagram. Across an LDR, light goes in, and light dependent resistor. Light going in, this is it. Sometimes you see them having a circle around them. This is what you need to draw. Your voltmeter gets connected like this, in parallel. You sometimes draw these little kind of small dots, they should be a bit smaller than that, to show that there's definitely a connection in there. It's a bit like a tube map. If you see 2 lines crossing, it doesn't mean that there's a station there, but if you've got 2 lines crossing with a circle, that means that there's a station. So there's definitely a connection there. That's a voltmeter, and it's across the LDR, 2 marks. Explain how the student can work out the resistance of the LDR using the circuit. Well, this is just read voltmeter for voltage, read ammeter for current, V equals IR VIR, so resistance equals voltage over current. Do your calculation. So, part B. Mark scheme is here as well, so if you want to have a look at what the mark scheme says as opposed to what I say, then you can do. The student shines the LDR through a circular hole in a piece of black card. The student repeats the experiment using cards with holes of different diameters. The distance from the card to the LDR is always 5 centimeters. Okay. The student varies the current in the circuit by adjusting a variable resistor. There's a lot going on. There's a lot of wordy stuff here. The independent variable in this experiment is, and the control variable. Okay, there are a few things we need to know. Independent and dependent variables. Think of it like this. The independent is the thing that goes in. It's your input. It's the thing that you change in order to get a certain type of output, and your output is your dependent variable. So your output is dependent upon an input variable which is independent. So your independent variable goes in, that's what you change. Your output variable is what changes as a result. Everything else you want to control. Everything else you want to keep exactly the same and do not change in this experiment. So the control variables are actually sometimes the easiest ones to work out. So the control variable in this experiment is the distance from the card is always 5 centimeters. So the distance from the card to the LDR is the control variable. The dependent variable, the one that goes in, the one that you are changing. You have to read this carefully. What are you changing? It says that the student shines a light on the LDR through a circular hole, and the student repeats the experiment using cards with different diameter holes. That's what you're changing, that's what's going in. So the independent variable is the diameter of the hole. That's the one that you are changing, that's the one that goes in. So independent variable goes in, the output variable is dependent upon the independent variable, and all the controls stay the same, do not change. And mark scheme is here. Photograph shows how a student places a metal ruler to measure the diameter over one of these holes. There's so many things you could say to make this technique better. And someone drew a really nice diagram. They actually had a hole like this. And they just drew a ruler like that. And I gave them a mark because it's obvious that they're saying move the ruler over the hole. And that's what it says here. Move the ruler to cover half the hole. Perfect. So that would have been worth a mark. You could even say, oh, if it says move ruler nearer the hole from the 0 on the ruler, if you just say start it from the 0 point, you don't get a mark. That's not good enough. That's to be ignored. So here we've got some data, and the next question is to make a graph. So I'm going to have a go at making this graph. Plot the students' results on the grid, and let's see. So we always start at 0. Don't do that thing they do in maths with the squiggly line thing. You don't need to do that. In most situations, you don't need to do that. So the diameter of hole, and some people started spelling hole W-H-O-L-E, even though it says hole loads of times, and with an H, hole with a W is a whole lot of stuff. A hole with just an H is that kind of hole. Don't spell hole wrong. Diameter of hole in millimeters. Okay, look at these. Look at the scale that I'm going to do. I'm going to choose a scale like this. I'm going to say this is 5, this is 10, this is 15. Remember that an axis is essentially a number line. 25 and 30 and 35. And that will be enough to fit all of this data. Some of you compressed this down and you had, that was 0, that was 5, that was 10, that was 15, that was 20, that was 25, that was 13. Stop there. If you use less than half of the space available, you won't get full marks. So that's why I've done it like that. So this is a bit easier though. You can just go up 1 centimeter is 100 ohms. So we've got here 100, 200, 300, 400, 500, 600, and so on. Remember, you need to include labeled axes. So this is the resistance of the LDR in ohms. Okay, already I've got 2 marks. 1 mark for writing down labeled axes, another mark for choosing the correct scale. 2 marks are available for plotting correctly, so 8 is 7.5, 8 is on here, and we've got to go to 10, 50, so I'm going to choose point now. Actually, I'm going to show you how I want you to do your crosses. I want you to do them slightly differently to this. I'll show you for the rest of them. 10 is 890. I want you to do a little line like that, so you definitely know it's on the 10, and 890 like that. So just rotate your crosses 45 degrees and make them like that. That makes it a little bit easier. 15, go all the way up, and it's around about 640 even, 640 is there. 20 is 490. 490 is about there. 20, oh, it doesn't go 25, it goes 23, which is here. 430. 430. And don't worry about your crosses being too long. It's the bit where it's a bit where the 2 lines cross that I'm interested in. 30 here is 340. Just there. Okay, that would get me 4 marks. I've plotted the points correctly. I've got my axes done. Draw a curve of best fit. I turn my my paper around like this because I know that if I draw with my arm, my elbow in one position, I'm going to end up drawing a curve anyway. So if I turn the whole paper to face me like that, I can try and draw a curve that goes through as many points as possible. If you're not sure about this, do it with a pencil. I've actually got too many points below the line. I should really try and do that again. I should have used a pencil the first time. We do it in black so you can see a better one in black. Okay, there you go. tries to go through all the points. Another thing to make note of: don't go before the last point, and don't go after. Don't go before the first point, and don't go after the last point. Try and keep the same number of points above and below the line. Either of those two lines would have actually been okay, I think. Describe the relationship between the resistance of the LDR and the diameter of the hole. Okay, most of you got 1 mark. I don't think anyone, actually one person got a second mark in this. Describe the relationship between the resistance of the LDR and the diameter of the hole. So, as diameter increases, resistance decreases. 1 mark. Don't talk about correlation. That's a word that they use in maths. You never see that in a mark scheme for science. So as diameter increases, resistance decreases. But it's not a straight line. It's not a straight line. Mention the fact that it's a curve. And say how it curves. Say as diameter increases, gradient gets closer to 0 or decreases. Something about the fact that it's curving will get you a second mark. So that's the mark scheme for that. I'll leave it there for a moment. If you want to, press pause. You can have a bit of a read of it. Non-linear relationship is what they're saying here. So that was question 5. Here's question 6. Question 6 is the electric motor. What's direct current? Current only flowing through one direction. Only flowing one way. What is the purpose of the brushes and the commutator in a DC motor? This is a really tough question because there's 3 marks available for this, and we don't go through it in a huge amount of detail because it's not actually on the specification in a huge amount of detail at all. So this is a very strange question that they've actually added, but it's here, so let's go through it. The first thing is to say they allow current to flow. And providing some kind of connection. So they're metal. And the second thing to say is what happens if there wasn't one. If there wasn't a brush and a commutator, then what would happen is that the whole entire thing would spin up to a certain point and then it would stop, because one side would constantly be trying to go up and another side would constantly be trying to go down. So you need to have the brushes and the commutator to basically flip around the current inside this coil here, so that the side that's at the top now wants to go down and the side that's at the bottom now wants to go up. And then when you get to that point again, instead of this bit always wanting to go down, the brushes and the commutator separate out and then come back together again to allow a reconnection. So this is kind of quite hard to explain in words, so let's have a go at it. They allow current to flow. Current in the coil causes one side to move up and the other down. We need the commutator to change the direction in the coil, so that one side, so that the sides that are being pushed up and down change. And then you could say something about this causes continuous spinning. Mark scheme says provides a connection reverses the current in the coil every half turn, reverses the field inside the coil so that the force is always in the same direction on each side of the coil, so that the motor keeps on turning. You only need to say 3 out of 6 of those points, but have a quick look at the mark scheme, see if that helps. The motor turns clockwise when the direction of the current goes from positive to negative. What happens if you change the magnetic field around? Well, that would flip it so it goes anti-clockwise, and then you change the current. Well, that would put it back to clockwise again, so it stays going clockwise. Because one thing would change it to go anti-clockwise, and the other thing would change it again to go clockwise. So two changes. It's like doing a U-turn and doing another U-turn. You're going to end up back in the same place. So it's clockwise. Here, photograph shows a machine at a coal mine. State an equation linking power, current, and voltage. There it is. Calculate the maximum power available from the motor. So the power is just going to be 600 volts multiplied by 400 amps. So you can use your calculator, or you can just do this in your head. It's going to be 2, 4, and how many zeros? 24 and 1, 2, 3, 4, 5 zeros. This is megawatts, which means million watts. And you're going to get the second mark for converting this correctly. So million, that's 1,000. That would be a million, so it would be 2.4 million watts. It's not million, it means mega, but 2.4. Gives you the mark. Question 7. Oops. Yeah, question 7. Student measures the circumference of a circular pipe, wrapping a length of string around the pipe 5 times, marking it with ink, as shown in the diagram, unwrapping it. So here, we've got that position there is 41.9, and what you have to do is use the photograph, estimate the circumference of the pipe. So obviously the pipe's been unwound. That was one position, and this must be the next position, so this will tell you the circumference of the pipe. That point there is actually quite hard to read. It's kind of between 47.3 and 47.4. Can you even see it on the paper? Let me just actually bring it a little bit closer, see if that works. So it's kind of in between 47.3 and 47.4. I'm going to say 47.3 because I know what the mark scheme says. And the estimated circumference is then going to be 47.3, take away 41.9, and what's that going to give you? Just use our calculator. I haven't got my calculator with me, which is not good, but I have this instead, which we'll do as a calculator. 47.3, take away 41.9, and what do we get? 5.4. Nice. 5.4 centimeters. If you do measure, if you do use the photograph and you read it wrong, you read 47.4, for example, you'll still get the mark because it allows anything in the range between 5.3 and 5.5. The student finds a total length of string for 5 turns as that. So all you need to do to calculate the mean circumference for the pipe using those values, you do 25.6 divided by 5. And that's pretty simple as well. So 25.6 divided by 5, what does that give me? 5.12. 5.12 centimeters. And that's exactly what it says in the mark scheme. That's fine. Here is a new way of measuring the circumference of the pipe. You measure the diameter using a caliper, and you don't need to know what a caliper is to be able to answer this question. Calculate the circumference of the pipe using the formula. The circumference is the diameter times pi. There's a trick here that a lot of people missed. That says millimeters, and the answer, they want it in centimeters. So first thing I'm going to do, so I'm going to remember that 1 centimeter has 10 millimeters inside it. So 15.1 millimeters is 1.51 centimeters. A lot of people miss that. So if we now do 1.51 pi times pi, 4.74. We'll just write it down as 4.74 centimeters, that's fine. Another thing I wanted to point out, I forgot to mention back in this question, 2 significant figures. Some people wrote down 5.40. That's 3 significant figures. And that means that you will only get 1 mark, you won't get 2. If a question says answer to 2 significant figures, make sure you do that. The student uses 2 methods to find the circumference. This is one method here, using the caliper, and another method using the measured length of string. Why do they give different results? They have given different results. This is a circumference, this is a circumference. Why do they give different results? There's lots of reasons. And we can speak about things that are specific to one or the other, and that's probably the best way to start it off. The first is, well, if we look at this again, back at this first question, we weren't sure exactly where that was because the thickness of the blob of ink is actually about 1 millimeter thick anyway. So when we talk about the string, I'm going to put things about the string over onto one side. The thickness of blob of ink, I've switched to a black pen, I'm going to turn back to blue. The thickness of the blob of ink might be greater than 1 millimeter, and that will affect affecting results. Also, another thing to mention is the string has a thickness itself. Now, because the string has its own thickness, that's going to add to whatever your value is for the circumference, because imagine that's your pipe and you have a piece of string going around it like that. Your string is actually a little bit further away from the pipe. The center of the string is a little bit further away, so the string has a thickness. The thickness of the string means circumference. Whoops, can't spell at the moment. Circumference will be higher than expected. Regarding the caliper, there are a few things you could say. That you could accidentally crush the pipe. If you pushed too hard, you could squeeze it a little bit. The mark scheme lists lots and lots of different things. There's a different precision. So the caliper is obviously to a higher level of precision than the string. Do not use the word accurate. Precision is important. Precision is how, the precision of an instrument is basically the smallest possible value it can give you. So use the word precision, not the word accurate. Accurate is how close you are to a true value. So if you had a thermometer and it measured that the temperature of water when it boiled was 100 degrees Celsius, then you would say that was a very accurate thermometer. If you had a thermometer that measured that the boiling point of water was 100.0000 degrees Celsius, you could say it's an accurate thermometer and it's very precise, because the precision is to do with the number of significant figures and the decimal places involved. Don't use the word accurate when you mean precise. You could say there's a calculation error. Things like the value for pi, someone made a mistake when they were calculating something. Unskilled use of equipment. So the calculation error applies to both, because for the caliper you have to multiply by pi, and for this one you have to work at an average. So the calculation error could work for either of them. Unskilled use of equipment, there's a load of information here about what could the unskilled use of equipment be. One of them I've written down, accidentally crushing the pipe. The width of the pen mark. The string could stretch. The thickness of the string will make the circumference larger. The parallax error, we speak about parallax errors a lot. 0 errors with the caliper, so when it's closed, does it actually read 0? It's a bit like going on weighing scales. You've got to make sure that they say 0 before you get on them. The pipe could be damaged, or the pipe might not be circular. One thing I want to avoid is human error. Don't say human error. Don't say it. Just don't even write it down. It's not worth any marks at all unless you really explain what the human error actually is. Don't just say human error. It doesn't get you anything. Okay, so that was question 7. Question 8. Okay, let's see if we can get this all done in under an hour. This is now part of the triple paper. So if you did double, you can stop now, I think, and we're just going to be pushing on with some of the triple questions. So, the man pushes a metal trolley along a corridor towards the left. Explain how the man gets electric charge. Friction between the wheels and the ground cause electrons to rub off. One and go to the other. So many people forgot to talk about electrons. Electrons are basically the key here. That's what causes things to have a charge. So, transfer of electrons. And the next question. Man presses a button to operate the lift. The spark, there's a small spark. Charge equals current multiplied by time. And that's the equation you need. Calculate the average current. So if you rearrange that equation, current equals charge divided by time equals 0.0017 divided by time, and the time is 75 milliseconds. So I'm pausing here because a millisecond is not what we want to use in our equation. We want to use seconds in our equation. So a millisecond is like a millimeter. There are 1,000 of them in a second, just like there are 1,000 millimeters in a meter. So we divide that by 1,000. So think about place value. Imagine there's a decimal point there. You go 1, 2, and then 3. So it'll be a 0.075. Now we can use our calculator again. And we have 0.0017 divided by 0.075. Let's see if that works. That's going to be a decimal point. Let's get rid of that and that. That's better. Ignore the negative sign. 0.022. So our current is 0.022 amps, and the mark scheme wants around 0.022 or 0.023. Metal appliances such as the lift button are earthed for safety. Explain why the man receives a shock even though the button is properly earthed. Why does the man receive a shock even though the button is properly earthed? Well, he's touching a metal. He's touching a metal button. So that's a conductor which will allow electricity to flow. And when he touches it, this is the button, and it's earthed. There's going to be a spark. The reason that there's a spark is because this is an easy path for electrons to flow to get to the ground. And imagine he's got lots and lots of electrons on him at the moment. They want to escape, and they're pushing apart from each other, and here there are no excess electrons. Here we've got loads and loads of extra electrons, more electrons than protons, which causes a negative charge. And what you want to do, all those electrons, they want to go down through that metal and move. And they can't move initially because he's got these rubber shoes on that's stopping any movement of electricity. Now he's going to touch something that's metallic, and the electrons can then finally move off him and go on to something else. Because they're pushing apart, and here there isn't any electrons pushing apart, we can say that there's a voltage difference between here and here. There's actually a voltage from one side to the other side, and that causes the electrons to want to flow. Mark schemes here, have a quick look, and press pause if you want. So this is question 9, even though it says question 1. So a digital signal is one like this. Ups and downs, and ups and downs, maybe a long up and a long down. 0 and 1. They only take 2 values. So that's what they're looking for. 2 marks for that. 1 mark for drawing these vertical lines, and 1 mark for just having zeros and ones. What are the advantages of using digital signals rather than analog? We spent a lot of time on this, so I hope that you got this right. I think most people got 1 or 2 marks out of this. No one got 0 marks. So the advantages of using digital signals rather than analog. The first is all signals pick up noise. But with digital, signals can have noise removed. Can have noise removed. Much easier than analog signals. So digital signals can pick up noise, like all signals, but digital signals can have noise removed. And that means that you can ultimately carry more information, have a clearer signal, which means clearer TV signal or radio signal, anything signal. So it basically means that you can do whatever you like to it. You can regenerate the signal, you can make it louder without adding any distortion. You can, or do all of that, but it's basically around noise. Noise is the most important bit. This is question 10. Almost there. Question 10. 2 properties of EM waves. Well, they all travel at the speed of light. All electromagnetic waves travel at the speed of light. What else do they have in common? Well, they're all transverse. They all transfer energy, like all waves can. Here, there's a few bits of information about just general waves. They can be reflected, or refracted, or diffracted. They can travel in a vacuum. That will work as well. Which of these EM radiations has a frequency greater than ultraviolet? If you can't remember this, you need to listen to the song again. Radio waves, microwaves, infrared, visible light, UV, X, and gamma. Increasing in frequency. So remember that these are the ones that we can use for communication. These are the ones that can be used for heating things and for cooking. And these are the ones that can generally be nasty and possibly cause cancer. The one that has the greatest frequency is gamma. Gamma's up there. Higher frequency than all the others. So, part B. Transformer. Supplying an output voltage of 2000 volts, alternating current to the wire grid. The input voltage was 230 volts, alternating current. So you've gone from 2000 to 200. Oh, no, you haven't. You've gone from 230 to 2000. You've gone up. So this is a step up transformer. What's the relationship between the primary voltage, the secondary voltage, the primary turns and secondary turns? We did this in the big transformer poster I wanted you to make. The voltage across the primary divided by the voltage across the secondary is the same as the number of coils across the primary divided by the number of coils across the secondary. There are 110 turns on the primary coil. calculate the number of turns on the secondary coil. So let's plug in some numbers. 110 turns on the primary coil, that's NP. We know VP and VS. They are, primary coil is the one that's the first one, the input one. 230 divided by 2000 equals the primary coil, we don't know yet. Oh no, we do know. It's 110 turns on the primary coil. The number of turns on the secondary coil, that's NS. We don't know what that is. So in order to work this out, that will get you 1 mark if you could do that. We have to rearrange. So we want to get NS onto the other side. So what we can do is we can multiply, actually one thing I'm going to do is going to invert the whole entire thing. If you, 1/2 equals 2/4, obviously, but if you flip the whole thing around, 2/1 equals 4/2. So you can just do the inverse of everything. And what I end up with is 2000 divided by 230 equals NS divided by 110. So if you want to, you can start doing the calculation now. I think a lot of people like doing the calculation straight away. So 2000 divided by 230, what do we get? That gives us 8.695. And what I want to do is to get NS now, NS divided by 110 gives us 8.695. So let's multiply the whole thing by 110. And we get 957 roughly. So, whoops, NS equals 956.5, and I'm going to write down 957 because when it comes to number of turns in a transformer, you don't usually deal with decimal values. And it says here 960, and 957 is fine. Cool. Suggest a reason why there is a plastic mesh. That's just on the outside of the device. It's to protect people because it's an insulator. I think almost everyone got that right, so I'm not going to spend any more time on that. This is the last question. And some people struggled a little bit, so let's go through a little bit slower. A boy has a mass of 43.2 kilograms. Lands on a skateboard with this velocity. So state the relationship between momentum, mass, and velocity. Well, momentum is P. P equals mv. The skateboard has a mass itself of 2.5 kilograms. Use ideas about conservation of momentum to calculate the combined velocity of the boy and the skateboard just after the boy lands on it. So the boy is taking a big running jump and jumps on the skateboard. The skateboard is still. So use your common sense for a second. He jumps onto something that's still, and he has this velocity. If it's flat ground, the velocity of them combined is going to be a bit lower than that. So imagine if you jumped onto a trolley, the velocity of you and the trolley would be lower than the initial velocity that you had initially. So what we need to do is we need to say momentum before equals momentum after. So momentum before is the running boy and the skateboard. Apologies for my diagrams. And the momentum after is the skateboard with the boy on top of it. So what was the momentum of the boy? Well, momentum is mass times velocity. So the boy has a mass of 43.2 and a velocity of 4.1. And that's going to be the momentum of the boy. I'm going to put it in brackets just to say that is definitely just the momentum of the boy. What's the momentum of the skateboard? Well, it's got a mass of 2.5, and the skateboard is stationary. It is stationary, so it multiplies by 0, so that's just going to be 0. Equals, what's the momentum after? Well, this is a bit more complicated because it doesn't tell us what the mass of this whole thing is, but it tells us what the mass of the boy is and what the mass of the skateboard is. So the mass is going to be, you add these two together. So we're just going to quickly do it on the side. 43.2 added to 2.5 equals 45.7. So 45.7 multiplied by the velocity that we're trying to work out. So all we need to do is calculate now. So that becomes 0, so we're not going to include it anymore. So we've got here, I'm going to use my calculator. If we have 43.2 multiplied by 4.1, what do we get? What's that? 43 multiplied by 4.1. Good. 177.12. In fact, if you had done that, you get 2 marks because it shows that you understand that you needed to work out the momentum. 177.12 plus 0 equals 45.7 V. So all we need to do now is divide, whoops, let me undo that. Divide that by 45.7 to get the value for V. So V equals, why does it come up as, we change it to a 4. Still try and change it to a 4. There we go, that's better. V equals 3.875. So the combined velocity, I'm going to say, is 3.9 meters per second, roughly. Mark scheme says 3.9 is fine, 3.876 is fine, that's good. So that's the velocity, and it's a little bit lower than 4.1, which is what I expected. The boy holds a heavy ball as he stands on the stationary skateboard and throws the ball forwards. What happens to the boy and the skateboard? So he's stationary now, he throws the ball forwards, he's going to start to roll backwards because he's throwing the ball forwards. So the boy goes backwards. Now it says you need to really, in the mark scheme you really need to speak about momentum. The reason why this happens is, again, momentum at the start has to equal the momentum at the end. Well, the momentum at the start is 0. It's the boy on a skateboard with the ball and not moving. The momentum at the end, well, the ball has the momentum. The ball is going in that direction. So I've already said to you that the boy is going to be rolling backwards, but let's speak a bit about why. So if you think about it, the momentum at the start is 0, and the momentum at the end has to also be 0. But it looks like two things have a velocity. The way that this works is you can have that total momentum be 0 because this is a velocity, it's mass times velocity, and velocity has a direction. So if this one had a velocity of 10 meters per second, you could then say that this velocity, I'm going to just make up a number here, we're not actually going to do any maths, is negative. It's negative, so 2 meters per second. A very heavy ball that would be. But because it's negative, you end up with something that's positive and something that's negative adding together, which could equal 0. So the way that you can explain this is by saying that if something moves forwards and there was initially 0 momentum, the only way that would work is if something else is moving backwards. So that's why the boy goes backwards to conserve momentum. Okay, it's the end of the paper. Well done. Look forward to seeing you guys on Friday. Bye.